Hey guys, we're back, and Ribby and I were out checking on the herd, seeing if any of the nebulas were going to give birth to a brand new star or not. And we kind of got to talking about binary systems and stellar deaths and supernovas and that bizarre stellar graveyard out in space. So we thought we'd let you guys in on some information. First of all, out here we got quite a few what I like to call binary systems. Yes, the ranchers repeatedly tell me that they are called cow-calf pairs, but I prefer binary system. So a binary system is two stars that actually orbit each other. While they were probably formed about the same time, they are different masses, and therefore they're at different stages in their life, much like these two up here. Now, the thing about a binary system is the more massive star will reach the white dwarf stage before the less massive star. And so what happens is you get this very small white dwarf that's very, very dense and has a very strong gravitational field. Well, when the other star gets to its red giant stage, it expands. And so it doesn't have the ability to pull on those outer layers of its atmosphere like it used to when it was a main sequence star. And sometimes what happens, if those outer layers expand enough, the white dwarf star will actually pull in those outer layers into its gravitational field, and it will gain mass. Look at all them binary systems moving together. Now, the thing about it is, a white dwarf can only hold so much mass before it hits what's called the Chandrasekhar limit. See, a white dwarf is supported by electron degeneracy pressure, and if it gets too massive, it can't handle it and it explodes into what is called a type 1a supernova. Okay? So when that happens, it is a supernova explosion, much like a high mass star supernova explosion, but it's called a type 1a or a white dwarf supernova. Now, a very, very high mass star will do what's called a type 2 supernova, or what people traditionally think about as a supernova explosion. And this is when it fuses heavier elements beyond helium, and it'll fuse elements up to iron. It won't fuse anything beyond iron because it takes more energy to fuse something beyond iron than it produces, so the fusion reactions will cease. It'll explode into a type 2 supernova. Now, if it's one of the most massive stars in the universe, it will collapse into what is known as a black hole. Now, a black hole is something whose gravitational field is so strong that nothing, not even light, can escape. Uh-oh, Ribby upset one of the stars. So here's what would happen if you found yourself in a black hole. Well, actually, if you found yourself in a black hole, you'd be ripped apart and you wouldn't know you were in a black hole. But let's pretend you're in a black hole and you have a flashlight. If you were to shine the flashlight beam up, it would actually go up for a little while, but then it would just come back down. Much like throwing a ball up on Earth. It would go up, and then it would just come back down. The beam of light would not be able to escape. Now, around a black hole is what is called the event horizon. Anything within the event horizon is a one-way trip. There's no escape because nothing is faster than light, and if light can't escape, nothing else has much of a chance either. Now, at the event horizon, the escape speed is roughly equal to that of the speed of light. Beyond the event horizon, you can escape if you're going fast enough. Now the other option, if you're not quite the biggest, baddest boy in the universe, the other option is to collapse into what is called a neutron star. Neutron stars are extremely hot, extremely dense, rapidly spinning balls of neutrons. They are supported by neutron degeneracy pressure, and they're about the size of a city. They don't produce very much light. Light can escape from them, but they don't produce very much light, and they have such a tiny, tiny surface area that they're not even on the HR diagram. They have extremely low luminosity, even though they're really, really hot. All right, Ribby. Well, it doesn't look like we're going to catch any stellar bursts right now anyway. So I guess that's it for today. Come on, Rib!